record. And write down the time, 12:34. And let me also connect my phone. Well, that's connecting. I can look up the problems again. Let's see, for your class. And you said 21?
Yeah, 21.
All right, that's as good as any. And oh no, that was weird. Oh, and I got a delay here. That's what's going on.
Did you construct like a mount for your iPhone?
Hey, what?
Like a mount?
Oh, well, it's I wouldn't exactly call it a construction, but I guess so. I took my wife has a selfie stick,
Oh, okay.
and I just mounted the selfie stick to kind of the shelf that's I don't know 14 inches above the table, and then stuck it out, and so I just mounted to the selfie stick looking down.
Oh, cool. That works out.
Yeah, and I think it's working pretty good. I wish it the only thing I'm disappointed with is really the it seems like on Zoom anyways that it's kind of narrow or not as big as when I make the video solutions, but maybe, and that's also maybe depends on your device, because I know like I use my desktop and my laptop, and my laptop's a small one, so it's pretty narrow, and then my desktop has got a bigger screen, not a ginormous one, but certainly much bigger than your any laptop. I don't think would make a laptop this big, and then and that looks good, but when I do the video solutions, it's in high definition, and then students can see it whatever size they choose their screen to be. Yeah.
Have you thought about putting the phone horizontal?
I tried that, yeah, and it didn't switch. I go, oh, that would, and yeah. Maybe I should try it a second time, maybe, because I did that the first time, and I was still just experimenting. So, but it didn't change the video on Zoom, and I didn't understand that. It changed it on the iPhone, but not on Zoom. And I was like, huh, that's weird.
Oh, that is weird.
So maybe there's something weird about it. Anyways, I'm going to stop the sharing for a second because there seemed to be a significant delay. And I'm going to try my connection again. And then meanwhile, I'll write down here. All right. So chapter 32, number 21. Oh, good. And it looks like no real delay there. All right. So 21 says we have a 140 millihenry inductor and a 4.9 ohm resistor is connected with a switch and a 6-volt battery as shown. All right, so here is the battery, and I'll just put 6 volts there. Looks like they've got a second branch with a resistor, and I'll put the number in, 4.9 ohms. Then we've got this little curly thing for our inductor, and they give us at 140 millihenries. And then they give us this single pole double throw switch. So here is A and here is B. And so A has a little metal conductor and B has a little metal conductor, and then we can move this sliding metal piece. called our single pole. And the double throw is we can put it either direction. So right now it would be making contact with A in my picture. And then I can slide it over and make contact with B. They show it right in the middle, but I kind of like it, at least connected to one or the other. All right, so A, after the switch is thrown to A, connecting the battery, what time interval elapsed before the current reaches 220 milliamps? All right, so one of the things that I hope you got out of the chapter, and maybe I'll do a little bit of it, but if you were to do the Kirchhoff's loop rule, which is a conservation of energy, you would get this 6 volts minus, and this is our new device for this chapter, something that gives us a voltage, but that voltage depends upon a changing of the current because the current makes the flux. So this is our inductor, so I'm going to call this minus L di dt. And then minus the IR 4.9. And if we can finish the loop, we get 0. Now, if you want, I can go through the calculus, but this comes out to be a current equal to, and then it's your maximum current. So maybe I'll just write I maximum. And the big piece was 1 minus e to the negative t over this time constant. So it's a lot like charging up a capacitor, although we're not charging a capacitor. We like to say we're energizing an inductor. There's not charges involved. And the maximum is kind of easy to get at because after a long period of time, this term right here is 0 because there's no more change in the current. Eventually it'll settle out to some what we would call steady state. And in that case, you would just have the 6 volts and then the IR. So the maximum current is just simply Ohm's law, 6 divided by 4.9. Okay, so 6 divided by 4.9 is 1.22 amps. So it will eventually get up to 1.22 amps. Now, the other piece of this is this time constant, which when we solved the same type of equation for a capacitor, it was RC. This one comes out to be L over R. So for this problem, the L is 0.140 henries, and the R is the 4.9 ohms. And a henry is a volt per amp each second. So the units here would be this volt divided by that ohm. Then this would be in the denominator, which I will flip and multiply, because a volt over an ohm is an amp, so that cancels off, and you're left with so many seconds, as it should be, because we're going to put a time constant. So that's why we call it a time constant as unit of a second. So 0.14 divided by 4.9 comes out to be a time constant of 0.0286 seconds. I'll put page 1 here because it looks like there's a lot of pieces to this one. And I guess I'm working on part A. All right, so with that piece of the puzzle then, let me rewrite this. So the maximum current is 1.22 e to the minus t, and then the time constant is this 0.0286. And we are asked here in A, what time interval elapses before it reaches 220 milliamps, which I'll write as 0.22 amps. And so now we have an equation with only one variable, time, and so we've got some algebra to do. Maybe the first one is to take 0.22 and then divide it by the 1.22. And so this is 0.180, 1 minus e to the minus t over 0.0286. Maybe I'll move the exponent to the other side. And then this over to the right-hand side. So this becomes 1 minus that last answer. So that's 0.8197. Now I'll take the natural log of both sides, natural log of the answer, so that this over here becomes a negative 0.1988. And this becomes a negative t over 0.0286. The two negatives would cancel off, and if I can just squeeze it in here, then time would be equal to 0.0286, and I've already canceled the negative, but it looks like a 0.005 and 69, or 5.69 milliseconds. So there would be A, how much time did it take to get there? Check my answer here in a second. But B says, what is the current in the inductor after 10 seconds? And this is kind of an interesting problem, because one thing we could do is just go back and plug it in. And I think I will. However, I think what they're trying to do is to also get you to do more than just plug and chug into the numbers, but kind of read the math there, kind of like that crazy song I sent to you this week.
Oh my gosh, that was hilarious. What was it, Doc Young?
Yeah, Doc Young, and I forget how they spell it. Was math. It wasn't math, it was math.
Oh my gosh. Yeah, that was hilarious.
And so, yeah, I didn't know if they were making fun of me or making just fun. I was like, oh.
That must have come out a couple years ago when that music, that style dubstep was pretty popular.
Oh, yeah. Oh, good.
Because it's gone out of style a little bit, so it dated the song.
Oh, well, good for you. You know your musical styles a lot better than I did. Yeah. Yeah, I think it was 4 years ago. So.
Yeah, sounds about right.
Anyways, but so to answer this B, one thing was really more, as I said, kind of understanding the math, making a connection to the physical world. 10 seconds would be an enormous amount of time compared to this time constant we did earlier. This is what is this? 1/400th of a second. So, 400 of these would make just about 1 second, and then we got 10 more of those. So we're talking about 4,000. So in other ways, this is really saying in this problem that we've reached steady state. This inductor is not doing anything anymore. This term has gone to essentially zero, and we would be at the steady state. We would be just ignoring this inductor. This would be like a straight wire, no voltage, because remember, we only get voltage when there's a changing of the current. So this current should just be the 6 divided by the 4.9, which gave us this 1.22. So my first reaction is just to say, look, after 10 seconds, it's 1.22 amps, the inductor, and we're in steady state. The inductor is, it would be the same as when they often say the switch has been closed for a long period of time. Now, on the other hand, if I actually do the math, it would look like this. It would be 1.22, It'd be 1 minus E, and so it'd be a minus 10 over that time constant, which would be 0.0286. And you can see that in the math. When you do a 10, and you divide it by 0.0286, oops, I subtracted. That wasn't good. Let me try that again. 10 divided by 0.0286. You're looking here at, well, I said this was 1/400th. I meant to say 1/40th times 10. So that's under 400. Yeah, okay. But E, where is E of my calculator? E raised to a negative of 349 is, oh, look at that. My calculator even gives me a 0. So it's even smaller than 10 to the minus 99, which then I would just have 1.22, 1 minus 0, which is 1.22. So that's what I was kind of referring to, that I think part of what the author wants in that question was really not for you to go through this calculation, but to realize that's just an enormous amount of time. 10, it sounds funny, 10 seconds is an enormous amount of time, but for this piece of electronics, it is. And so that would be the current after a long period of time.
Could you solve for the t that is on the line of like just getting to be a long time?
Oh, sure, yeah. Of course, we would need a definition. What is your, definition of t near a long time? Is it like 1%? Or I guess the current's building up. So maybe I'll do that. Actually, in statistics, usually when you get to 99.5%, you consider it full. So that's kind of a good side question. I like it. Here, I'll solve for it. So it's not C, but you might say something like, okay, what is the transition to a long period of time? What time would it take to get to 99.5% of the maximum current? So there's the maximum. I'm going to take 99.5% of it. And of course, it makes my math a little bit easier if I write it as a 1.22 on each side so I can cancel it off. So that means when I move the E to this side, I get something like this, and then I get 1 minus 0.995, which is 0.005. So then when I grab my calculator and take the natural log of 0.005, it looks like I'm at about 5 time constants. And that's actually kind of the normal procedure in exponents. It says 5 time constants is pretty much there, and you can see 5 time constants is 5 constants is probably 99%. And so 5 time constants, because each time constant is only 0.0286. So I would define anything greater than this, 0.15 of a second, to be a long period of time for this circuit. So anything greater than 150 milliseconds.
Okay, interesting.
Yeah. So what's a long time is kind of relative to what you're working with. So for a circuit like this, anything greater than 150 milliseconds is a long period of time. Which obviously taking a test, 150 milliseconds is not a long time to take a test. Okay. So yeah, great question. Now let's go to the C here. It says, now the switch is quickly thrown from A to B. What time interval elapsed before the current then falls to 160 milliamps? Now, again, I'll say the same thing. I can go through the calculus if you want, but when something is now de-energizing, just like the capacitor, we could write it out, and we would have only the inductor. We would have that term. We would have this term. We wouldn't have the 6. And instead of a 1 minus e to the t over tau, we got something that said I is equal to its initial value, e to the minus t over tau. So it's a de-energizing of the current. And so again, just like the capacitor, we charged it up, and then we also could talk about discharging it. The solution is essentially the same. So in this case, that's why it was important to at least do B, noting that we had left it long enough to get to a current of 1.22. And so that's going to be my starting current. My definition of starting is starting once I move it from position A over to position B, it's now going to be draining its energy. And so it would start at 1.22 and then exponentially decay. Now the time constant is still that same equation, whether we're energizing it or not. So this would still come out to be 0.0286. And we're asked to find the time when it gets to, and I'm going to write it in amps. So instead of 160, I'll put 0.160. And now we've got some algebra to do. So 0.16 divided by 1.22 gives me 0.1311 on the left-hand side of the equation, and e to the minus t over 0.0286 here. And so taking the natural log of that last answer gives me a negative 2.03. So it's about 2 time constants. And each time constant is 0.0286. So taking that 2 and multiplying it by the 0.0286, 2 time constants, we're looking at 0.0581 seconds. So about 500, 600 of a second.
Okay. If we were given like the same question but a crazier circuit, how do we get those equations? Would we do like a Kirchhoff's thing?
Yeah. I think you're asking, okay. Let's do then. If nothing's pressing in the chat, let me turn on my chat. Oh, good. Yeah, let's do then. I'm kind of looking at the second page here, because this would actually be a good answer to your question, that I got those equations because, they happen to match the one that was solved in the lecture, I think is what you're saying.
Mm-hmm.
And I was saying, well, I could resolve it for you. But I think even better is what you asked is, why don't I not solve exactly the same as in class? Because number 59 would be a really good example of that. I'll even put this in the notes here. Let's start number 59 here at 1258. Because watch, let's do exactly what you said. You're right. I would just write out the Kirchhoff's loop rule. And so exactly what you kind of said here, I just did the loop rule and I got the equation. And I didn't bother on this video to solve it because I had done it in the lecture and the textbook had done it. But let me actually solve one, and then maybe it's a little different than this, so you'll have more. And so, yeah, I like that a lot here. So let's do that. Let's go to 59. Although I don't want to take the joy away from you struggling through it. I don't know if that's
It would be like a system of equations, and we'd probably at one point
Yeah.
have to refer to survey for the solution.
Yeah, so you're going to have a system of equations. Now, part of the reason I was thinking is it might be good to see this is it will be a system of equations, I think. I don't think it'll be an easy solution. I think it will be a whole system. But, let me put here, chapter 32. But it won't be an algebra system of equations. It will be a system of equations with a differential in it.
Yeah,
And
that concerns me.
yeah, and so it's neat to see it, but it won't be that hard.
Is there a table of those?
No. Well,
No.
let me just say that well, I should just do it because I think I alluded in the lecture that anytime we have a differential equation, we have the easiest kind, which is separable. And once you can separate it, then you integrate it and you're done. And so those kind of differential equations you probably saw beginning in Math 160. Whereas harder differential equations like second order or, well, there's a lot of just harder ones. That is what Math 220 is all about. So you aren't required to, know your Math 220 for this class. So anyways, so everything we give you, and this is one example of that, is you'll see that I just have a separable differential equation, and I can just separate it and integrate it.
But it might take a few like substitutions from the system to get there.
Yeah, right. So there's only one of them that's going to have a derivative in it, and then you substitute the other one in, and so you end up with this, one equation after that with only one derivative. So if we had an inductor in both loops, then we would have, a derivative in each equation. And that, depending on how it is, might be more than would be fair for a hard one. But that's not what we have.
I was going to ask, if you're going in the direction of the current and you encounter the L, you would mark it as a negative?
Yes.
If you're going with the current?
Yes, good point. Yes.
Okay.
Yeah, but it's because and I'll put it here, when we worked this out, it would be in section 1 of chapter 32. We started with the physics that was called Faraday's law. And in the last chapter, as we did Faraday's law, we just said if there was a change in flux, and many of the problems that we had in chapter 31, the flux came from some other device, and then we were looking for the EMF in another device. So we often said, like, okay, we have a coil over here that has current, so that's the primary, and then it induces a flux and makes an EMF in a secondary. But in this chapter, I tried to point out that the current in a coil would make a flux that would go through itself, so it would make a voltage on itself, and that's why we refer to these as self-inductions, because it's their own current that makes its own flux that is then interfering or creating a voltage within itself. And so what we've done is we've said that all this flux calculation is made out of a bunch of other things, like how many loops, how big are they, and then the only thing changing with time is the current. So if we put all of these things that have to do with what I call geometry, the number of turns, the length of the solenoid, the diameter of the solenoid, and we put that together with this n, then we all call that all together the n, and then we just have a di dt. But what I was getting at in all of this long conversation here was this negative out in front is technically there. And you said put a negative when you go with the current. I wanted just to say it's already there. This is Faraday's law. This negative in front of it is the mathematics of Lenz's law. Remember, Lenz's law says it opposes a change. And so if the current is increasing, then the voltage is negative. If the current is decreasing, so that's a negative, then together with that negative makes that a positive. And so Lenz's law, when we use it in words and say we oppose the change, that just means in mathematics, it's the negative of whatever the change is. So you write down what the change is, and the change could be positive or negative, and then you put the negative there.
Okay. I wanted to ask because I haven't seen an example where it's crossed the coil going the other way.
Right. And but if you did, yes, you would change the sign of that.
Okay.
But why don't I just, write out the equation for this one, and then, but I will go with the current, and I will use then the voltage on the inductor, and I will then use the negative.
Okay, makes sense.
Yeah. Okay, so coming to this problem now, let's see what it says here. It says that at time equals to 0, the open switch in figure 59 is thrown closed. Using Kirchhoff's law for the instantaneous currents and voltages of the two loops. So they're kind of helping you on this one, because like you said, we solved the simple one, but we didn't solve something quite like this. And so they're giving you the clue on how you would solve it. Show that the current in the inductor for time greater than 0 is given by this equation. And it kind of looks like what we had before, when we had just one resistor and one inductor in series. However, it only includes one resistor out in front, but both of them in the time constants. And in addition, they have this weird form that looks like something you'd get when you're looking at something in parallel. But let's just show that that's what it would look like. So I would draw the circuit, and following their advice and really kind of our discussion here is, let's write out, like we would do in chapter 28, a system of equations. But because we have the inductor, this system of equations is going to have a derivative, at least in one of them. And so making a circuit like this, and again, if I was just maybe going back to chapter 28 and thinking of this as a resistor, I might say, okay, well, coming out of the battery is current number 1. It goes across this switch when it's closed. It hits this node. Then the current goes down resistor number 2. So I'll call that current number 2. And then the rest of the current goes around this loop with the inductor, and I'll call it current number 3. And so the first of my 3 equations would just be saying current number 1's got to equal number 2 and number 3. That's our node rule. That's our conservation of charge from chapter 28. And so that would have to be true. Then we could do our loops. So let me do the easier loop, the left loop here. We'll take this battery, which they call script E. So I'll go from here to here. That's a plus script E. Then I'm going with the current. So it's minus I1 R1. I go through the switch. Then I go through this resistor. So minus I2 R2. And I complete the loop. So that's the first of our 2 loops. And again, just kind of going on what, like we did in chapter 28, we would do each loop, the left loop and the right loop and the node rule, and that would be our 3 equations. So doing this loop, maybe I'll start down here and go against the current. So this would be a plus I2 R2. And then when I get to my inductor, and this is kind of what you said, I'll be going, with the current. So it'll be a minus L di, and in this case, the current would be number 3. And so how current number 3 is changing, and that would complete the loop. And this is the part that kind of started our conversation, is see, now I have a system of equations. 3 equations, 3 unknowns. The 3 unknowns are current 1, current 2, and current 3. We're asked to find the current in the inductor, or where? Where is this? Use Kirchhoff's rule. Show that the current in the inductor is given by this. All right, so we want to solve this for current number 3. And so I guess I would suggest then maybe holding off on the last equation. It's got the derivative in here. Because why don't we look at the first 2 and eliminate current number 1? So if I take and merge together these first 2 equations, I would have the EMF minus, in place of current 1, I put current 2 plus current 3 times R1 minus current 2 R2 equals 0.
Oh, did your thing freeze?
Oh, it did.
Oh, too bad.
I wonder why, but let me reset it here. Okay, so stop. Let's see, my phone's still working. Okay. And here we go, looking good.
Seems like there's less people last week than and this week than there have been all semester.
Yeah, and last week I kind of suspected, because you guys had just taken a test, and and I really hadn't graded much. Oh, in fact, by that point, I don't think I graded anything, and yeah. But today I did kind of think there'd be quite a few people, and there's just you 2 here, so interesting.
Yeah, I'm like just starting the homework now, so I'm kind of here just to listen.
Well, yeah, and and that's kind of what I'm thinking. Maybe that's what happened. People, this is the time in the semester in a traditional setting, anyways, where it just becomes overwhelming for students, and I know that in a traditional setting, instead of getting a little chit chat at the end of the lab about November, this is when people, they come in, they do it quick, and they take off. There's no chit chat. There's not to say people don't ask questions, but very few. They stop and come up to my desk and say, "I got a question on this." All right, thank you. Got to go. So I think that same thing's going on, and given your yeah, and it probably really depends on your other classes and when the tests are, because in this class, your next test isn't for a while. So it's very easy to say, I better get going in my math, and I'll skip physics for a little bit.
Oh, I noticed 34 was to be assigned in the syllabus. How deep do you plan on getting into 34?
I'll say about halfway. Off the top of my head, I can't remember what sections those are.
Okay.
Yeah, and I better not say off the top of my head, but I'll look at it. You could even, if you wanted to, jump ahead on the video lectures 234, and I think I say it one day at the beginning and just say, well, we're not gonna test you on, and I want to say sections 5, 6, and 7, but I'm not real sure if that's it.
I think I'm nearing the end in the YouTube playlist.
Yeah.
I think in fact, I think I might recall that there's only one lecture on 34.
That very well could be true. That's why we only do a part of it.
Also didn't see any homework solution for 34. So are we just gonna get taught it and then not have homework on it?
Solution or assignment? Because I'm gonna go through and I'll pick some sections that you should do.
Just according to the syllabus, it doesn't have any like numbers for 34.
Yeah, so I guess I need to start thinking about it. Here's what I normally do, and I same thing is that when we get towards the end here, I'll see which sections we cover, and then as you'll see in the lecture, I kind of go through. I said, well, we'll do something like this and like this and like this, and so as far as studying, look at the problems at the end of the book where it says these are from section 1, these are from section 2, these are from section 3, but don't turn anything in. We're just at the end, and so I don't officially assign anything or have you turn anything in.
Okay.
But like what Doug did for 121 is he taught like fluids, but and there was some homework on it, but it wasn't tested.
Okay, and but yeah, I'll probably go close to that, but not exactly, because there's just some fundamental ideas of the problems from 34 that they're pretty basic. They're plug and chug. It won't overwhelm you, and that's what I want to make sure people don't see the last lecture and they get overwhelmed.
Mm-hmm. Is 33 as difficult as 32?
Yeah.
The homework, I did not like what you just asked, Gina.
What?
Yeah, if I say yes, am I going to scare you to death?
Okay, fair enough. Yeah.
On the plus side, it's really the 33 is really the same as 32.
Okay. Something about 32 is throwing me off.
Okay. But I think it'll sink in for you. And
okay. Yeah. It usually makes very little sense my first time through. So I guess.
Yeah. And that's normal. Yeah, they're very normal. And I would describe 33 as really just like 32, except for our power supplies aren't a constant value. They also have a time factor in there. And so like this problem we're halfway through on, I would have an equation that over here would have an E in it, and it would have a function of time. So now I'm going to have a function of time and a derivative.
Sounds calculus.
And well, right. So you got quite a bit of calculus in there, and of course it also then kind of helps to make sure you're doing more than just doing the math. You're kind of looking at what is the physics, reading the math of why there is a back EMF. Yeah.
I realized when I got to this class, I'd never read math before in my life.
Okay. Well, it's
I thought I was good at math until I actually had to sit down and read it.
Yeah, it's interesting too, and I've had students, bright students, but they're math students and they're a math major, and they come in here and they're always a little surprised. They're like, "Oh, I won't have any troubles with physics. It's all math." And I was like, "Okay, I hope so." And
right.
they get a little bit of a rude awakening at times. Like, whoa. Yeah, they're not always. In fact, I was on. I think Daniel. I think you were there the last Friday's discussion.
Oh, I didn't make it at all last Friday.
Oh, uh, oh, no, it was Anthony. Sorry, I mixed you guys. But what I was talking about is I was on a panel last week for one of the clubs. It was the
Society of
Industrial and Applied Mathematics, right?
Yeah, that sounds right.
Oh, I went to the club meeting. I heard you talk. Yeah.
Oh, okay. So you were there. Yeah. So, anyways, but I did find it. He said it real quick, and I might have been the only one who caught it. But when Gabe was doing his talking, he said something very interesting. He said that when he was doing his optimization math for his, I think it was his PhD, he said he was noticing one of his friends or colleagues who would do this insight into the math because he saw how the math was connected to the physics. And it caught my attention because I was like, yeah, so he was able, and Gabe was saying, guy, that was so neat how he was able to make large steps without rigorous proofs, but they were nonetheless true because he knew how they applied to the physical world. And I was like, in my mind, I was like, yeah, that's what I keep trying to tell my students. We do half these problems with math, but we do the other half of the problems with the physics, especially a lot of these flux calculations. It's like, boy, save yourself a lot of math. Look at the physical picture of what's going on. And you don't have to do so many hard calculations. So anyways, I digress. Hopefully I didn't lose too many of you. All right, Gina, I'll continue on here. Mm-hmm. So back to the system of three equations. Like I said, I'm going to deliberately avoid the one with the derivative for a moment and combine these two. And this is where the camera froze. So what I did is I took this total current one, and put it into equation number 2 and just rewrote it. So this would say E, and then this would be current 2 R1, current 3 R1, current 2 R2 equals 0. Because now, if I rearrange it, minus current 2, there is an R1 here and an R2 here. And then there's a minus I3 R1 equals 0. And my second step is going to be, let's solve this for current number 2 and now put it into here. And so what I will end up with is an equation that only has current number 3 in it. And it has a derivative. So I'll have to do a separation of variables and integrate. So I will write this as E minus I3R1. And moving this to the right-hand side, this would be current 2 over R1 plus R2. Moving the R1 plus the R2 to the other side, I now have an equation for I2. And so this is what started this conversation here is, yeah, I'm going to have an equation that we have not solved anywhere in the book. You're kind of on your own for it. But it is nonetheless a system of equations. And now I can do the last step of this system of equations, take current number 2, which I just got by combining equations 1 and 2, and now put it into here. So let me put equation number, or current number 2. So this would be script E minus I3 R1 over R1 plus R2. That's current number 2. And then, of course, times R2 equals, and if you'll let me just save another step, and now I'm going to move that one to the other side. So the L's over here, and then the DI3 DT.
I'm sorry, can you?
Let me go back to this. I do too many steps, sorry.
I'm just trying to follow the substitution. So we solved for I2 and then we plugged it into that third one of the originals?
Yeah, right there, perfect.
Okay, okay.
And that's how I got that term.
Okay.
And then, yeah, good. And then this term I just moved to the other side, so it's a plus. Good. Now, if you look closely at it, you can see the only unknown is the I3. That's good. That's what we're asked to solve for, the current in the inductor. And we have something that is separable. It looks like we did for the inductor. It also looks like what we did for the capacitor, the charging inductor. I'm sorry, I shouldn't say charging, the energizing inductor, the charging capacitor, and also for that matter, air friction back in physics 121. And so there, and here's how we did that. We said take everything that has the same variable with it, which would be, say, I3, and put it together. So since this has an I3, let me move that numerator into the denominator so that everything with the I3 is on my right-hand side of the equation. And everything that has the other variable, which is time, I'm going to move to the right-hand side of the equation. And the constants don't matter what side you put them on. I've already got the L on this side, and I've got the R1 plus R2 on this side. I could put those together on the left or the right-hand side, or leave them separate. I think I'll just leave them separate since that's where I am right now. But the big piece that I think you were asking about is, what do I do when I get to a differential equation? Well, as long as it's separable, all you've got to do is put everything that was a factor of t on one side and everything that has the I3s on the other, and then integrate, and you're done.
Was that R2 on that numerator supposed to be multiplied through?
Oh, I bet it was. Thank you.
Sure.
Yeah, that would have been a big mistake. Thank you. Let's see. It would have been I2 would go here, and then I multiply it and be both terms. Thank you. Thank you. How about I do, and let's leave it out. Maybe I should have just left it out. How about that? All right. Yeah, I'm going to do that and see what that gets me. In fact, I'll then pull it out in front since it's now a constant. Because again, my attention is really focused on the stuff that has the I3 in it. Okay, so now I can do an integration. So let's do this. Let's say that, as the problem says, the switch is closed at time equals to 0. So let's go from 0 to some moment in time. We'll just write it as a variable. I could do 10 seconds, and I think it would probably be an easier looking problem. That's kind of what you're used to in your calculus. You see this, 0 to 5 or 0 to 10. But I'm just going to go 0 to some variable t, which means the other integral, which is integrating the current, would be, what does it start with? And of course, since the switch is open, we can argue that it would start at 0 currents, and after a period of time t, it would go to some current I. And that's what we're trying to solve for. What is the current I after a period of time t? All right, so this integral's pretty easy. This just becomes r1 plus r2 multiplied by t evaluated from 0 to t. And then this one is maybe a little bit harder to see, but since this is downstairs, you can see that it's going to be a natural log. But of course, then the chain rule means there's got to be extra factors that cancel off. And so what I like to do is the reverse. I like to say this is going to be the integration. But when I took the derivative of it, I would get that downstairs. But then the chain rule would give me a negative r in the numerator. So there must be a negative r1. Whoops, it's off the screen. A negative r1 in the denominator here. And let me just check that out. Maybe I should have just done a u sub, and then that would have popped out of the u sub. But I think this is right. So I'm just going to check it by taking its derivative. So I take the derivative of this, I would get 1 over, okay? And then the chain rule would give me a negative 1 over r, or would give me a negative r1, which would cancel with that, and I get just back to that. So perfect. And of course, let me not forget my limits. So this would be from 0 to I. So on the left-hand side of the equation, this just becomes r1 plus r2 times t, and then minus 0. That's kind of boring. Now this over here, I will put that constant, the 1 over negative r, together with this. So that's a negative L r1, r2. And then I'll do this. And so this would be the natural log of e to the minus I. And so when I put in I for I3, I get that. And then minus when I put in 0. And when I put in 0 for I3, I just get the natural log of script e. Okay, now I can see where this is going. If I move this over to here, I have a negative R1 times R2. Oh, I'm so silly. This was over 1. And then a T. Over 1. Over 1. Almost messed that up. Okay. All right. So that's, let me make that clear. Okay. So that's this integral over here. And I did the R1 and the R2. What I do with the L? Let me put the L there too. And then this side just becomes natural log, and like all of our fun natural logs, let's take the difference between two natural logs and write it as a quotient. We'll only have one natural log. And then that way we can then raise it to a power of e, do the anti-log. So when we do the anti-log, we get e to the negative. And if you'll let me come back to the original question, they say let r prime be the 2 multiplied together and then in the denominator added. So they tried to make things a little simpler in their writing by putting R1 and R2 in this fashion and call it an R prime. So that's good. So I'll do the same thing to save myself a little bit of writing. And on the right-hand side, I would get E minus I R1 over E.
Is this
So,
I3 we're working with, or
is this what?
is it still I3?
Yes. Maybe I should have left it back here as I3. Back here I said just let it go from 0 to I.
Okay.
But maybe I should have said still call that I3. So my limits would have been I3. And so when I put it into here, it would have been I3 and I3. Some people don't like to use the same variables for what you're integrating as what your limits are, because that can be a little confusing.
Okay.
But at the same time, that's what we wanted to represent. So I'm never sure which was better. So I just left it as an I because that's how they had it here. They had it as just an I. So I was like, okay, I'll just do an I.
Can you help me read the math of what integrating from 0 to I3 means?
Oh, yeah. Okay, so this would be, an integration. We're saying it builds up to. So this is saying we're getting a little bit of current in our inductor, and it builds up. So the delta I3 is say this is the increase in current. So you start with 0 current and you add a little bit more, and then you add a little bit more, and then you add a little bit more, and then you add a little bit more. And so after a period of time, you would have built up to this total current of I3. It would be like saying this delta, this is a little bit of current I'm adding to you. So it'd be like me or your employer giving you a quarter, and then another quarter, and another quarter, and another quarter, and another quarter, and another quarter. And after a period of time, let's say an hour, if they kept giving you a quarter every half second or something, then at the end of 1 hour, then this I3 would be your total amount of money that you have. So this I3 is now the, I'll put I3 here. This I3 is now the total that you would have at the end of this, adding up a little more and a little more and a little more. And my example of adding a quarter is probably not a good example, because the whole integral involves something in the denominator that keeps getting here. Well, I should say keeps changing as it builds up. So you might say something like this. This little piece right here, if I was reading the math, would be something like, okay, I'm going to pay you, how would I say this? Every minute, I'm going to pay you half the amount towards a total of $10. So in the first minute, this little piece would be $5. You're like, ooh, I'm going to make $5. Yeah. All right. But then in the next minute, I'm going to give you a little more increase. But my increase is a function that changes. And so what I'm going to give you is half the amount towards your $10. So let's see, that would be $2.50. So the next minute I give you $2.50. So now your total is $7.50. Yay. Okay. Now the next minute, I'm going to give you half of that. So that's $1.25. So now I give you $1.25. All right. So you add that to it. So what are we at? $8.75. So after 3 minutes, you've got $8.75. You know, like, wow, 3 minutes of work. I got $8.75. I'm going to be rich before this day's over. But each time we only give you half towards the $10. So no matter how long you do this, you're only going to eventually end up with $10. And so it's not a very good financial deal to work all day for $10. But the first 3 minutes was great.
So time goes from 0 to t, and then like, you have to consider the bounds of one when you do the downs for the other?
Yeah. So this is a what in math you'd call a definite integral. And so if the question was more narrow, if the question was this, what is the current after 1 second? This side of the integral, you would have gone 0 to 1. And so you would have said, let's add up the current for 1 second. So that's what this side is saying. And so this I3 would be the current you would get after 1 second.
Okay, I understand now.
So yeah, okay, good. So in this case, I'm just saying, what is the current after t seconds instead of 1 second? So I'm using the variable as the limits of my integral.
Okay.
I guess that's what I should have said for you. Okay. All right, so getting close to finishing this system of equations with a derivative in it, I now could move the script e over to there, and I get this minus r prime lt, and I get this e minus I3 r1. Then when I move this over to here, it becomes a positive I3 r1. This becomes the script e, and then minus the script e to the minus r prime lt. And one last step then, current number 3 would be I'd factor out a script e and divide by r1 and get 1 minus e to the negative r prime lt. Yay!
Okay.
And that is exactly what they wanted to get. But as you can see, at least even if you didn't follow all the math, but it sounds like you did because you stopped and asked me some good questions. You didn't even caught my one mistake or 2 mistakes. You caught one of my mistakes. And then, fortunately, I caught the other one before I went too far. But this, is just a set up a system of equations. So I would say, in theory, we could give you any complicated inductor and resistor. You could write out the equations and you could solve them. Although obviously solving the math, some of them are easier than others. Fortunately, they are all separable. So really, there's any kind of configuration you would be fine with. Some easier than the others, and that's why in the lecture part of this, we did the ones like in the last problem where the inductor and the resistor were just in series with each other. This one, as you can see, the math took a little bit longer now that the inductor and the resistor is in parallel. In fact, not only parallel with each other, but also then an added resistor is in series with the group. So this turned out to be a little more complicated. And of course, that's why they combined R1 and R2 together in some kind of equivalent resistance of it.
Okay, so a first step might still be to find R equivalent, if you can reduce it at all first.
Yeah, if you can, but did you notice I couldn't in this one? So
right.
don't mix those two. Yeah. So if I had this, if R2 instead of being here was actually maybe in line with it, so they would be series. Yeah, I would have just put R1 and R2 together and called it equivalent and said, well, I have one resistor, one inductor. We solved that in the book and in class, and I know what the answer to that is.
Looks like next chapter they throw some capacitors onto the circuit.
They do that before this chapter's over.
Oh, really? Okay.
Yeah, they say, because right now, let's see, I don't think you asked me any ones with a capacitor in it yet. Nobody has, but yeah, there's a capacitor thrown in with the inductors, and then the last step of this chapter is to throw all 3 together, and only in series. That's it. That's as far as we go. You start doing them in parallel or some kind of more complicated connection. they get really hard. And so we would want to learn other techniques. And at that point, we are going from a circuits class, from a physics class into a circuits class. In fact, there's a bunch of people in this class who are also in the circuits class. And I'm sure that's what they're doing right now. They're learning techniques on how to do the inductor no matter where it is.
Oh, so this problem asked for the current in the inductor. So we could also solve for I2 and I1.
Oh, yeah, good point. So now that we've got the current in the inductor, we could come back to this equation we got earlier on page 1 that said, what is the current in number 2? And so we could put this equation in, equation number 3 into here and get the current for number 2. And then, of course, once we have 2, we can add it to 3 and get the total current in the battery or resistor number 1. Yeah. So, and that's a lot of exercise in algebra, and apparently, and I probably agree, the author doesn't think it's worth asking that as a part B or C. If you got this far, you got what they're after, that you could, in theory, solve any problem. You just write out Kirchhoff's equations. Just now, the 3 equations have derivative, or at least in one of them. And harder ones would have derivatives in the other ones, but you still have a system of equations.
Okay.
Mm-hmm.
Great answer. Really thorough. Thank you.
Oh, good. Yeah. You never know if to be thorough or quick. And like going to the.
Yeah. You only get to pick one.
Yeah. Sadly, it's true. Actually, I saw a great sign in an automotive repair shop one time. It said, how'd it go? You could have it.
Done right or done fast, something like that.
Yeah, but it was even better because it had 3. It was fast, cheap, and right.
Oh, there's a quote about buying a car.
Yeah. Okay. Yeah, I think it was buying a car.
A fast one, a cheap one, or a reliable one. You only get to pick 2.
Yeah, and you could get 2 of the 3. It was good. But
yeah. So I bought a Toyota Camry, so I chose my 2.
Okay. Right. Right. All right. All right. Well, that was a good problem. It took us a while, but we had fun getting there. And I didn't see any other questions. So any of the other guys, let's see, where are we on time? 1:47. So got about 13 minutes before break time. I got a theory here on my virtual background. I think I'm going to try something here. I can't tell, but I'm holding my glasses up. But yeah, I think never had this before. I think the sun has gotten lower in the sky. And because it's got right there, lower in the sky, the light's coming in at a different angle. And when it catches my glasses just right, it forms an image that the camera picks up, and it's picking up my screen in the back. So if I have my glasses on and I turn, maybe the time of day changed too, but it was showing up real easy an hour ago.
Yeah, I've never seen that before.
No, and I I think this is an optics. This would be better next semester when we do optics, but I think it's taking the image from my window, and I'm nearsighted, so I think it's making an image that's probably about the same depth as my face, and it's picking it up and displaying it on the, however the, because this virtual backgrounds are pretty creative. They seem to be able to figure out the depth, and they don't pick up things behind me. Like if I back up, well, I think it picks up the nearest thing, but no. Yeah, so I'm about the same distance as the window now. It's picking up my my blind. I don't know. It could be I have my laptop at a different angle too. That's might be true because I think I got my camera tilted different, and then so I moved my laptop a little bit. Maybe that's more it than. I'm gonna change my laptop back so it doesn't really point towards my side window. It points behind me, my bookshelf, which I like my virtual background so you can't see how messy my bookshelf is.
You're in the living room?
Quick question about the final angle in question 3.
Question 3? Okay.
Yeah, like I got the 18.8 volts, but I don't understand how they got the 3.77 theta for the theta times time.
Okay, I'm gonna have to go back. You said question 3, chapter 32?
Yeah, question 332. I just don't understand how they got that final angle in the solution.
Okay, maybe I'll jump to the solution then. Let me read the question though. We have a 10 millihenry inductor carries a current of blah, 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 blah. What is the self-induction? Oh, okay. Oh, this, okay. I think I see where this is going. We have a sinusoidal current, okay. And then let me scroll to the answers here. Number 3.
Like how?
How'd they get the 377?
Yeah, wait. I think I just.
Yeah, they just put in pi 3.14.
Yeah, okay. I didn't even think about doing that.
Yeah, it's one of these things where, yeah, when you're working in radians, it's kind of nice to leave things in pi. So 120 pi is nice, and the math part of me says that's great. But then 377, it's nice to have a number because, to be honest, I'm not real sure off the top of my head what 120 times pi is.
Well, it's 377.
Well, yeah, okay. Right. And actually, that's a common number that at some point you should probably commit to memory because our voltages in our North America here are 60 hertz. And if you want to do a cycle, then, omega is 2 pi times the frequency. So 2 pi times 60 is where they got the 120 pi, and then 120 pi is 377. So anytime you see a function that has something like sine or cosine 377t, you're working with 60 hertz, and you're working with the standard power line in North America, Caribbean, a couple of small islands. The rest of the world seems to have settled in on 50 hertz. So.
Oh, Canada wouldn't have the same as North America. Well, I mean, I guess
North
America.
Which?
Canada.
Oh yeah, Canada's North America. Yeah. So Canada, United States, Mexico, actually share power grids. And so they've all uniformed on 60 hertz, so they can send power from, just like we send it from one state to another, we'll send it from one country to another. if you know, just like exporting power is good for your bottom line. If you're a company, you're trying to sell power, so you can sell it to Canada, and then you've got a bunch of people in Idaho who want it. Yeah, send it to Idaho. Then it becomes it's interesting business game too, because then you got hydroelectric dams that are in Idaho and Oregon, but they'll pay more in California. So you send the power down to California because you can make more money. Then you're short power in Idaho, so you bring it in from Canada, and now and Canada's got so much water and hydroelectric. They're like, you can get it real cheap. So you can get cheap power to the people in Idaho, and then export your power from Idaho to California and make money. So I guess that's really no different than any marketing. I mean, somebody buys a pair of jeans at wholesale, then they resell it to somebody else at retail, and that middle person just ups the price, and that's how they make their money. Yeah. Although in that case, I think there's some value added, because in a retail store you have a place to go, and hotel, the wholesale, it's just a big warehouse of boxes. So. And,
Professor?
Yeah.
Is magnetic, is there a chart of magnetic energy density in the book? Problem 24 plugs in a value, and I wasn't sure where they got it. For labeled U naught.
Oh yeah. Oh, looks like my camera's gone. I'll try to start it back up. But the energy density is the magnetic field squared over 2 mu naught. See if my phone.
1/2 b squared over.
Yeah. If you want to go 1/2 b squared, and if it's free space, which pretty much everything we're doing is free space, it's mu naught.
Oh, okay. I remember that from lecture now. I apologize.
Okay, yeah. So that one's that one's on number 24. That one's a little more straightforward, where it just says calculate it, and they give you the field.
Okay, cool.
Yeah. Oh, and then the second half of that is, then now if you have the energy density, you just have to multiply that by the volume, and you get the total energy.
Okay. Makes sense. Can I ask what the class average has been so far? Are we performing about as expected, or better, worse?
I think it's around normal, but to normal to better than average. So yeah, so the scores are a little better than, and this is kind of a gut feeling from me. I'll explain in a second, but they seem to be on average about normal, but maybe a high side of average too. So a little better than the normal class. I mean, so you guys are extra geniuses, I guess.
Does the fact that we're scoring a little bit higher have implications for future exams?
No.
Okay.
No. No. If it may have implications for future classes, if there's a lot of talk about keeping classes online once the pandemic is over, if it's good or bad, I got to admit, I started this whole pandemic thinking, oh, this is not going to be the best way to do physics. But I'm kind of curious what, and you might even see a survey from me or later on, because I'm kind of wondering if the future might not be something like this. Instead of having two sections of class meetings, we change it to one section of class meeting and one section of online, and students can kind of pick. I certainly don't want them all to be online. I don't see that as a good thing. I think there is, and I don't know how many who really need the benefit, want the benefit, have the structure of in-class setting. But there might be more than I thought before the pandemic who could actually, this could work out in a way that they like and in a way that works for them. The class part I get, the lab part I really wish you guys, were in lab holding the voltmeter and the ammeter and hooking it up yourself. I mean, that I don't think we can substitute online, no matter who you are. And,
yeah, I feel like in lab, I'm just kind of collecting data rather than actually doing the experiment.
Yeah, so that's probably my biggest, bummer about the pandemic. Although, I always got to keep it in stride that better that than we're all spreading coronavirus around to each other, and particularly our elderly parents, and people are dying. So I get it. So I'm not complaining that we shouldn't do it differently, but I am saying when the vaccine is finally approved and distributed, and my guess would be somewhere around April, we'll probably all be vaccinated.
That's optimistic.
That, I hope I'm not too optimistic here.
I hope you're right.
But purely speculational guess, but that's kind of what I'm thinking, that April we'll see. And even before April, I think we'll see the like frontline workers being vaccinated, the ones at risk, and then the elderly.
I go to this forum where people discuss where to invest. It's amateurs, and it's usually, I'd admit it's mostly poor quality submissions, but just the other day I saw a thread where someone suggested investing in syringe companies because they anticipate a vaccine to come out.
Mm-hmm. Yeah. Okay. Yeah. So syringes and and my thoughts too is a number of these vaccines would be packed in dry ice. So I wonder if ice companies are just going to have a field day of trying to supply all these ice. I know that in our experiments, like Santa Barbara Ice Company there on Milpas is where we get it for our labs. They're going to be just fighting all over the country trying to get enough dry ice to get these distributed.
Oh wow, yeah, that's worth my money.
Yeah. So, but anyways, that being said, so next fall, I don't know. I'm kind of thinking, that we, might have, and like I said, I don't know, but maybe the thing to do is to have everybody has to go to a lab, but you can sign up for either an in-class lecture or just keep going with the video lectures. And having those two options for the video lectures is maybe something to do.
I think your video lectures are really high quality, but I don't know if that's like standard across. Because I took a chem class and it was video lecture and it was not so efficient.
Yeah.
Okay.
Yeah, Danny knows. We went through the same thing.
Did you take it this summer?
Yeah.
Yeah. So it's I don't know what to. So who knows what the kind of the future holds. But I do think, though, that, as I said, that anything we do online in the future will be volunteer, and optional. Anyways, but I was going to add to your comment, Gina, that part of that is because, I've never used Canvas before. And so just like you guys have never learned this way, I've never taught this way. And, and I'm slowly getting the hang of Canvas. I mean, sometimes I make a mistake, like when I accidentally send the test out the day before the test. that was just stupid. But I just didn't understand what Canvas was doing. I thought, I don't know if I told you, but I thought it said you could put it in this file and it'll just sit there, so that then when this window opens, this is what I thought. So when the window opens, the students won't have to click on something and go to like my hard drive like I did with the other test. And some people had troubles with that because they didn't log into their school account. And I go, oh, this will be better. I'll just put it in Canvas in this little file, and it'll sit there. And when the window opens, then the students can access it through Canvas. That's how I understood it. But apparently,
it worked for me, though, because I went to click on it and it was locked. So.
Oh yeah, and so that's right. For you,
it's a good strategy. Something must have went wrong.
So something, anyways, it was weird. Anyway, so that was a mistake, just of lack of experience with Canvas. But I say that because I have another problem with Canvas that I don't usually have, and that is when I can't keep grades. I usually just did it in a spreadsheet. I would do an Excel spreadsheet, and then if I wanted to calculate averages, I could. It was no problem. But with Canvas, they have you guys broken down by your lab sections. And so it's like 10 individual classes for me on Canvas. And so I have to, like when I give you guys the test, I have to load it 10 times. Now, with that said, last week, I did some searching and found out how you can merge those 10 together as one. But they also said, don't do it during the middle of a semester because you lose all the scores in the other classes. So you make one the master one and merge everything else, but they have no way of transferring the work over. Anyway, so what I'm going with the idea that I just have to continue the rest of this semester with treating you guys as 10 individual classes. And sadly, then, I do not know what the average is of all 10 of them. Although, now that I say it out loud, maybe I should do this. I can find the average in each of the 10 individually, find out how many students are each one, do a weighted average, and then calculate on my own what the average is. So I guess that wouldn't be too hard to use that 10 pieces of information and get a net average for everybody. Maybe I'll still do that. But the point is, I don't have just an easy column like I did before at the bottom of my spreadsheet that just said class average.
How many questions are on the final? Is it 5?
Yeah, it's still 5, yeah.
Okay. Is there going to be like an emphasis on later material, or is it going to be truly cumulative?
It's truly cumulative, yeah. It's what do I usually do? I usually do a 2 from the material in the first, 2 from the second.
Oh, really?
And one from the third, or maybe I don't do something, but obviously with 5, I can't go 2, 2, and 2. I go 2, 2, and 1, and that depends. Yeah.
Okay.
Yeah.
All right. I think I'm going to do some more homework now. Thanks again for all your help.
Okay. You bet. Oh, yeah, it looks like it is break time too. So good. I need to use the restroom and get some food. So I'll take a break here, Daniel and Gina, and if you come back at 3, I'll see you then.
All right. See you in an hour.
All right.
Bye.
Bye.